So now we have a method for constructing a power series of a function. And let's just skip back to it. What we found is that if a function has a power series representation, then the power series has to have coefficients which are given by the nth derivative of the function over a over n factorial. Now if you read this closely, you'll see that the sentence has been structured in such a way that's actually very important. It says if f has a power series representation, then its coefficients are given by this. This does not say that every function has a power series representation. It just says if the function has a power series representation, then these are the coefficients. Now the distinction here is really about intervals of convergence. I want to know that if I take a function and I construct a power series for it, using these as the coefficients, I would like to know, does that series actually converge to the values of the function? In some sense, is the series and the function equal, and for what values of x are they equal? This is a question about whether the series does represent the function on a given interval. And that's the question we want to answer now. So we just looked at constructing power series representations for the exponential function and the cosine function, but there we didn't make any mention of the fact that we have convergence, that this series, if I plug 2 into this series, for example, how do I know that this series actually converges to e squared? How do I know that the interval of convergence for this series isn't -1 to 1, and that's only where it represents e to the x? How do I know that for other values of x it doesn't represent e to the x? So these are the questions, these are the subtle questions that we want to answer now. And so a bit of terminology. The nth Taylor polynomial, or the nth degree Taylor polynomial of f at a, is just obtained by truncating your Taylor series at n. So only taking the terms corresponding to 0 all the way through n and stopping there. And that's a polynomial now, and that's called the nth degree Taylor polynomial. If we take the limit as n goes to infinity of the Taylor polynomial, then that gives us just the Taylor series. The remainder of the Taylor series is defined to be the difference between the actual function and the nth degree Taylor polynomial. So you take your function, you subtract off your nth degree Taylor polynomial, and that gives us the remainder of the Taylor series. Okay, so what would it mean then for the series to converge to the function? Well, if this thing was supposed to converge to the function, in other words, it was supposed to represent the function, so if I plug an x value in to this expression for the series, I should get the same thing as the function value. What that means is that the remainder, the difference between the function and the nth Taylor polynomial, that should be getting small. That should be going to 0. And that's what we have as a result here in terms of our theorem. It says that suppose we have our function, which is the nth Taylor polynomial plus the corresponding remainder, to using that Taylor polynomial as an approximation to f. Then if the limit of the remainder goes to 0 for x minus a smaller than r, so on this interval about a, remember that just indicates that we're looking at an interval centered at a, where we go off r units in either direction. So the interval we're interested in is this interval here. So for x in this interval, if the remainder goes to 0 as n gets big, then f is equal to the sum of its Taylor series on that interval. So the question of whether the series represents the function and on what interval is really a question of, does the remainder go to 0 for x values in that interval? Now, in order to help us answer this question, to try to figure out when this remainder is going to 0, in other words, when the series represents the function, we've got an inequality known as Taylor's inequality, which tells us how big the remainder is compared to the function. And so what we want to do is to show any specific function has a power series representation, we must prove that the remainder goes to 0. And the facts that we're going to use is this connection between the higher order derivatives and the corresponding remainder, as well as this other fact that says if we ever encounter a limit of the form x to the n over n factorial, then it goes to 0. This really just follows as a consequence of the fact that the sum of x to the n over n factorial is a convergent series for all x. You can use the ratio test if you want to show that. So this is just an easy consequence of that, which you can look in the textbook. They prove this in the textbook, so you can certainly look that up in the textbook to see the argument. What we're going to do is we're going to use Taylor's inequality to show that the remainder goes to 0 for some of these different functions we've just constructed Taylor series for. The exponential function, the cosine function. We need to show that the remainder goes to 0 for those things in order to guarantee that the series actually does converge to the function. So let's see how we can do this. So in each of these examples, we want to show that the limit as n goes to infinity of Rn of x is equal to 0. We want to show that the remainder goes to 0. In fact, we want to show, since each question is asking us to show that the series representation is true for all values of x, we want to show that the remainder goes to 0 for all x in R, for all real numbers. So let's start with the first one, the exponential function. Okay, let's see what we need. Again, going back to Taylor's inequality, we want to show that the remainder is going to go to 0 as n goes to infinity. That means we need to show, for example, that this expression goes to 0 as n goes to infinity. But m, this big M, is an upper bound on the nth plus first derivative. So that's our starting place. Let's try to figure out what the bound is on the nth plus first derivative of our function. And we only need to bound it on some interval, d. So let's go to work on that. So what we'll do is we'll let d be any number bigger than 0. We're not going to specify what it is, it's just any number bigger than 0. And that's the interval we're going to work over. And we're going to see later that it doesn't actually matter what we choose d to be, because it'll work for any d. Now, since fn plus 1 of x, the nth plus first derivative of our function, in this case our function is e to the x. So the nth plus first derivative is just e to the x for all n. We have that fn plus 1, the nth plus first derivative of x, is bounded above by, well, it's actually equal to e to the x, and that's bounded above by e to the d for x values smaller than d in magnitude. So we've bounded the upper bound. So we're just looking at some interval, x values smaller than d in magnitude, and we've just bounded the nth plus first derivative on that interval. So now we have, by Taylor's inequality, with m equal to, well, m is the bound on the nth plus first derivative on the interval, so that's e to the d. A, in this case, our series is centered at 0. We're looking at the Maclaurin series. So we have that the remainder we have by using the nth Taylor polynomial, the difference between the nth Taylor polynomial and the actual function is given by this remainder. And we have, by Taylor's inequality, that this remainder is bounded above by e to the d n plus 1 factorial x to the n plus 1 on this interval that we're considering, x values of magnitude less than d. Now, we want this limit as n goes to infinity of the remainder to be 0 in order to guarantee that the series converges to the function. So let's look at what the limit is. That's e to the d n plus 1 factorial over x to the n plus 1. I can factor out an e to the d, and that becomes the limit as n goes to infinity. I've already factored out the e, so that's x n plus 1 over n plus 1 factorial. And what is this limit? Well, one thing to observe is notice that the only thing that we needed d for was to bound the derivative, and now that d appears out here. It has nothing to do with the limit. And this limit, by fact number 2 on the previous page, this limit is 0. So that's e to the d times 0 by fact number 2 in that Taylor inequality box. Just skip back to it. This fact right here. The limit of x to the n over n factorial as n goes to infinity is 0. So we're going to use that. And e to the d times 0 is 0. And so what we found is that the limit as n goes to infinity of the remainder is 0 for x values of smaller than d in magnitude. But, and here's the interesting part, but d was any arbitrary number. D was arbitrary. We didn't specify what it was, we just said it was some number bigger than 0. And so this means that the remainder goes to 0 for any x. If I want it to go to 0 for x being 1,000, well then I'll just take d to be 1,001. If I want to show that the remainder is 0 when x is 1,000,000, well I'll take d to be 1,000,001. The argument here did not depend on d at all. It turned out that d was arbitrary. We still get that the remainder is always going to be 0 no matter what d is. So d was arbitrary. So we have that the limit as n goes to infinity of the nth remainder of x is 0 for all x in the real numbers. So we've shown that the remainder goes to 0 for any x. And what does that mean? It means that the series has to converge to the function because the remainder is going to 0. So let's get back to that again, previous page. Previous page, one more. What we've got here is that we're trying to write the function as the nth degree polynomial plus a remainder. If we can show that the remainder goes to 0 for x in an interval, in this case our interval is going to be all real numbers, then we have that f is equal to its Taylor series. And so that's what we were able to conclude here. So therefore, e to the x is actually equal to its Taylor series, x to the n over n factorial. N goes from 0 to infinity for all x in R.